Today we finish our last two topics in the Unit 5, in the gases, and we're going to discuss two things primarily. One is, how do gases behave when they're in reaction? So we're going to blend together two things that we know. One, the gas laws that we've just learned, and two, the stoichiometry that we learned in previous units. And then secondly, we're going to take a look at what happens when gases are mixed together. This is very common in real life. Air, for example, that we breathe isn't just one gas. It's a combination of gases. So how do their pressures behave, and how can we deal with that? If we take a look at reactions like this one, hydrogen and oxygen combining to make water, we find that when their pressure and the temperature are constant, the mole ratios that we've used in stoichiometry, we could pretend that they're volume ratios, and that would work out just as well. For example, in this reaction, 2 moles of hydrogen react with 1 mole of oxygen, but that could also mean 2 gallons of hydrogen react with 1 gallon of oxygen, or 2 milliliters to 1 milliliter, or 2 liters to 1 liter. So all of those ratios of moles to moles also work for volumes. What are the conditions? They both have to be gases, and the pressure and the temperature have to be the same for both gases. So let's say we had this question to answer. How many liters of oxygen, this is a prediction, are needed to combine exactly with 1.50 liters of hydrogen? Both gases are at STP. So we know that the temperature and pressure isn't changing. They're both at STP. So we can use this idea of volume ratios to solve this problem. What do we know? 1.50 liters of hydrogen. What do we want to find? We want to know how many liters of oxygen. So in the middle, we can put a liter ratio. 2 liters of hydrogen to 1 liter of oxygen. And we find that the answer is 0.750 liters of oxygen. Mole ratios and liter ratios work the same. Now we can deal with gas stoichiometry in reactions even if not everything in the reaction is a gas. It's fairly easy to do. If some of the reactants or products are not gases, what we can do is we can use the ideal gas law to convert back and forth as we need to between moles and volume. Like in this example. This is saying the combustion of octane, C8H18, and octane happens to be a liquid. What volume of oxygen at this pressure, 740 torr, and this temperature, 32 degrees C, reacts with 250 grams of octane? So here we're not given any volume information about octane because it wouldn't make sense. It's not a gas. Let's see how we can do this problem. First thing we'll need is a balanced chemical equation. So I'll start out with C8H18 plus oxygen. And my products, because it's a combustion, are going to be CO2 and H2O gases. To balance it, well, I put a 8 here for the carbon, and then I could put a 9 here for the hydrogen. 9 times 2 is 16, 16 and 9 is 25, but I can't balance an odd number with an even number of O's, so I'll start this over again. And this time I'll put a 2 in front of the octane. 2 times 8 is 16, so I'll put a 16 in front of my CO2 to balance carbon. 2 times 18 would be balanced by 18 in front of an H2O. 16 times 2 is 32. 32 and 18 would be 50, so I can balance oxygen now by putting a 25 in front of my O2. Well, now let's get to work on the stoichiometry. What do we know? We know this, that we're starting with 250 grams of octane, C8H18. And where we want to end up is how many liters of oxygen. That's our ending point. Well, we can't go straight to liters because octane is a liquid and oxygen is the gas. So we're going to have to find moles first and then use the ideal gas law to provide us with liters. So let's do some stoichiometry right off the bat. First of all, the molar mass of octane, it's 114.232 grams per mole. So with grams down here, I have now moles of octane, and I can do stoichiometry. The ratio is 2 moles of octane to 25 moles of oxygen. Moles of octane cancel out. I'm now at the units I want in my answer, moles of oxygen. So I do my arithmetic. The answer turns out to be 27.36 moles of oxygen. But that doesn't answer my question because I'm supposed to figure out how many liters of oxygen. Well, I know this. PV equals nRT for any gas, including oxygen. So I can solve this problem for V and plug in the moles for N that I just calculated. So V is equal to N times R times T divided by P. Well, R I always know. N is the answer I just got. The temperature here is 32 degrees C. I can't put degrees C in here. That's got to be in kelvins. And my pressure is 740 torrs, but I can't put torrs in there. That has to be in atmospheres because of the units on R. So let me do those conversions. 32 degrees C plus 273 is 305 kelvins. So that's what's going to go in my T. And then pressure. Well, I've got 740 torr. That's the pressure of my oxygen. And I want to convert this into atmospheres, knowing that 760 torrs is the same as 1 atmosphere allows me to make this conversion, and my answer comes out to 0.974 atmospheres. So that's what's going to go in for P in my equation. So now I'll just finish this off. N is 27.36 moles. R is always 0.0821 liter atmospheres per mole Kelvin. Our temperature, we just found out, is 305 kelvins, and that's all divided by our pressure in atmospheres, which is 0.974 atmospheres. Unit-wise, everything goes away except liters. Atmospheres cancel there, kelvins there, moles there, and we get a volume in liters. The answer is 703. This problem is almost the reverse. Combustion of octane, C8H18. What mass of octane produces 500 liters of carbon dioxide at STP? Now we're given a volume and we want to find a mass. Well, it's the same balanced chemical equation. Here's our given information this time. We know that we're going to produce 500 liters of CO2. What we want to know is what mass, how many grams of octane would be needed. I can't go from volume to grams here. That's not possible. I can't even go from volume to moles without using the ideal gas law. So here's my strategy. First, I'm going to find out how many moles is 500 liters. Then I'm going to use stoichiometry to find how many grams of octane that corresponds to. So N, number of moles of carbon dioxide, is going to be equal to PV divided by R times T, because PV is nRT. So I can plug in my pressure. It said my pressure is standard pressure, 1 atmosphere. The volume is 500 liters. That's given to me. R is always 0.0821 liter atmospheres per mole Kelvin. And the temperature is standard temperature, which is 273 kelvins. The only unit left here is moles, when the liters, atmospheres, and kelvins drop out of the equation. If you do your calculation, you find out that it's 22.3 moles. There's a second way I could find this answer, and that is to recognize that this is at STP. And at STP, 22.4 liters always corresponds to 1 mole. So I could have also done this. I could have said 500 liters, and then used a conversion factor of 22.4 liters per 1 mole. And this also would give me 22.3 moles. Now remember, you can only use this conversion factor when you're at standard temperature and pressure. Otherwise, it's not going to work. Ideal gas law, you can always use no matter what the temperature and pressure are. Well, now that I know how many moles of CO2, it's a stoichiometry problem from here. Starting with 22.3 moles of CO2, I want to end up with grams of C8H18. The mole ratio is 16 moles of CO2 come from 2 moles of C8H18, and the molar mass of C8H18 is 114.232 grams per mole. When I do my calculation, I should have 3 significant figures here, and it's 318 grams. That's my answer. Our last topic is called Dalton's Law of Partial Pressures. John Dalton, the same person who gave us the theory of atoms, also did a lot of work with gases, and one of the things that he found was that in a gas mixture, a mixture of unreactive gases, gases that aren't going to do a reaction with each other, the total pressure is the sum of the individual partial pressures of the gases that are in the mixture. You could write this way. You could say the total pressure is equal to the partial pressure of gas A plus the partial pressure of gas B plus the partial pressure of gas C plus dot, 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 depending on how many gases you have. Air would be a good example of something that's a mixture of unreactive gases. In air, the total air pressure in a room, let's say, is equal to the pressure exerted by the nitrogen in the room plus the pressure exerted by the oxygen in the room plus the pressure exerted by whatever argon is in the room and CO2 and water vapor and all the other little things that are in the room. So if you were to take all the nitrogen out of the room, for example, and just leave the other components, the pressure would drop dramatically because air is mostly nitrogen, and its pressure contributes the most to the pressure of air. It's like thinking about all these particles bouncing around inside of a container. Some of them are nitrogen molecules, some are oxygen molecules, some are CO2, some are H2O, and so on. And all of their collisions, no matter what type of particle they are, contribute to the overall pressure. You just add them up. Well, a place where this shows up very often is when we collect gases over water. Take a look at this little video clip. Here what you see is some gas from a cigarette lighter being put inside of a cylinder, and that cylinder is originally full of water. So you can see the bubbles of gas coming out of the lighter, and because gas is lighter than water, it goes up to the top, and it creates this space up there that's filled with the gas from the lighter. The lighter gas that was collected in the video we see here in this picture, and it sums up into this space that we see in the top of the graduated cylinder above the water line. This is an example of what we call a wet gas. Here's why we call it a wet gas. Imagine if you took a pan of water and you set it on a table and you walked away and came back a week later. If the water was shallow enough, there would likely not be any water left in that pan at all because it all evaporated. But we think about evaporating as happening out of open surfaces like a pan of water. But in a closed space like this space here, evaporation also occurs. And so water comes up from this water line and evaporates up into this closed space. Now eventually it'll be too crowded and the water molecules will stop evaporating, or at least the total number of water molecules in the space will become constant. There's also gas in here from the lighter, obviously, and so what we have inside of this space is something that is described by Dalton's Law of partial pressures. So for wet gases, we can say this: the total pressure is equal to the pressure of the gas from the lighter, in this case, plus the pressure of the water vapor that went up into that space. Now, water vapor pressure changes. As the temperature goes up, the pressure of the water vapor at equilibrium also goes up. But it's not a straight line relationship, as you can see from this graph. It's shallow at first, but then it gets steeper and steeper as the temperature increases. Here's an interesting fact. When you're at 100 degrees C, which is the boiling point of water, the vapor pressure is 760 torrs. Not a coincidence. We can talk about that later. So, because this isn't linear, there isn't any quick, easy equation we can use to calculate it, but we can look it up in textbooks and other kinds of references like online resources. So we'll have to do that when we solve problems that involve water vapor as a part of a mixture, in other words, wet gases. Like here's an example. Hydrogen gas, it says, is created by reacting hydrochloric acid with zinc. If 7.50 liters of hydrogen gas is collected over water, and the pressure is 1 atmosphere, temperature is 25 degrees C, the question is how many grams of zinc reacted. Now this is a sort of a complex question because it's gas laws, it's partial pressure, and it's also stoichiometry. Let's take a look at solving it. First of all, let's write down all the things that we know. We know that the volume of hydrogen is going to be equal to 7.50 liters. We know that this is happening at a pressure of 1 atmosphere, and we know it's happening at a temperature of 25 degrees C. And since none of these gas laws work with Celsius temperature, let's just change that right away by adding 273. We know that our temperature is 298 kelvins. It would also be helpful to know what the pressure of water is, because this is a wet gas. This is a gas collected over water. And so that means the pressure of hydrogen isn't really that 1.00 atmospheres. That's a total pressure. The pressure of hydrogen is going to be 1.00 atmospheres minus the pressure of the water that has evaporated up into the hydrogen gas. Well, let's go online and just find out what the pressure of water is at 25 degrees C. Do a quick Google search. Let's just say water vapor pressure, and we'll take the first resource that comes our way. There's a nice little chart that gives us degrees Celsius in this column and torrs, or millimeters of mercury, in this column. Go down to 25 degrees C, and there it is, 25 degrees C, 23.8 torrs. Let's go back to our problem and insert that in the right spot. Well, this is atmospheres, and the pressure that we found on the internet is in torrs, so let's just rewrite this. Pressure of hydrogen is 1 atmosphere, but we also know that that's 760 torrs, minus the pressure of water, which it said was 23.8 torrs. What's the difference? Well, the pressure of hydrogen is 736 of those 760 torrs. So that's the pressure that we'd have to use when we do our stoichiometry problem. Okay, next, balanced chemical equation. Well, it says that zinc is reacting with hydrochloric acid, which is HCl, and it's producing hydrogen gas, obviously one of our products, but it's also going to produce a second product, and that'll be zinc chloride. Zinc is 2 plus, chloride's 1 minus, so that's ZnCl2. To balance it, we need to have a 2 there. Alright, so if I have 750 or 7.50 liters of H2, and the question is how many grams of zinc will I get, I have to do stoichiometry, but first I've got to change these liters into moles, and that's going to be done with the ideal gas law. Well, N, number of moles, is equal to PV divided by RT, and that's how I'm going to be able to do this. Now, if I want number of moles of hydrogen, then I have to use the pressure of hydrogen here, which we just calculated, and that's going to be 736 torrs. But I actually can't use torrs either, can I? It's got to be in atmospheres in the ideal gas law. So I'll take this 736 torrs, and I will change this into atmospheres using this factor. 760 torrs is 1 atmosphere. This gives me a pressure of 0.969 in atmospheres. So let's plug that in for pressure. 0.969. I'm going to leave the units off as long as we're consistent. We know it'll work. 0.969 atmospheres. The volume is in liters. We don't have to convert that. 7.50. R is 0.0821 liter atmospheres per mole Kelvin. And the temperature here is 298 kelvins. So we've put all of our units in correctly, so the answer that we get numerically should have a unit of moles. When we calculate it, we find that it represents 0.297 moles, and that's 0.297 moles of hydrogen that are in that 7.5 liters. Well, we're nearly done. It's just a stoichiometry problem from here. So we'll take that 0.297 moles of hydrogen, and we'll use stoichiometry to convert this into grams of zinc, which is what the problem's asking for. First, I do a mole ratio. In the balanced chemical equation, 1 mole of H2 is formed from 1 mole of zinc, and that will give me moles of zinc, but I want grams of zinc, so now I need the molar mass. For zinc, that's 65.39 grams per mole. That converts me into grams of zinc, and my answer is 19.4 grams of zinc.